Well met, my friends. Lesson 3.3 is action-reaction pairs. And by that I mean we're talking about Newton's third law. You've probably heard it before. They usually say for every action there is an equal and opposite reaction. But in physics we need to define those a little better. What is an action and what is a reaction? So what Isaac Newton was really talking about was forces. Really, the way we're going to say it is for every force, there is an equal and opposite force. So anytime something is pushed, something will push back. Let's write that in. So that's Newton's third law. For every force, there is an equal and opposite force. The calculations for this are actually going to be pretty easy because the equation is only two letters. We can represent this by saying F1 equals negative F2. But try to remember what this negative means. This negative is the direction. So basically this means if something is pushed right, if this is a rightward force, the opposite force will be pushing in the left direction. So what we can do with these is, if these are the only forces, we can plug in MA. So I'll add that here. If no other forces are present, we can plug in MA to each of these. So net force equals MA, not individual forces like this, but if there are no extra forces, if there's only one force acting on each object, then the net force will be F1 and F2 respectively. So we could go like this. And then F2 would be M2A2. So when two things are pushing on one another, the forces are the same, but the difference will be in their accelerations. So if M1 is larger than M2, for example, then A1 would be smaller than A2. So if you have a very large, massive object that's being pushed, it'll have a small acceleration. And if you have a very small object being pushed by the same force, it'll have a very large acceleration. So that's why we talk about for every force there's an equal opposite force, because it makes it, I mean, saying action reaction makes it sound like there's the same acceleration. So the challenge here is identifying the forces. The math is really easy, as we can see here. The equations are really simple, but figuring out what the forces are is sometimes a little tough. But we got a simple way of doing it. Here's the trick. To identify the force pairs, to identify the force pairs, swap the nouns. To identify the force pairs, just swap the nouns. For example, every force can be summarized in 3 words. What is pushing what? So here's our first one. Here's our action force. If you were to stand up and push on a wall, we would just say student pushes wall. And the nouns here would be student and wall. This is obviously our verb. So if the student pushes the wall, the reaction is that the wall pushes student. And you can tell this by, if you were to push on a wall, you lean back a little bit, or at least you feel a little bit of resistance. So all you do is swap these. The word in the middle stays. It'll be either the phrase pushes or pulls, and you just swap it around. So we know that when you push a wall, the wall is going to push you back with the same exact force, but it pushes you in the opposite direction. So if you were to push on a wall, you might fall backwards. Let's see a variation of this. So a force is either a push or a pull. We're going to look at a pulling force here. Truck pulls trailer. That's what Isaac Newton called the action force and the reaction force. Swap the nouns. Trailer pulls truck. Now, admittedly, these two are pretty boring. Nothing really groundbreaking there. But the reason I show you this is because you can always do this. With any force in the universe, you can just swap the two nouns that are present, and you will have a true force that actually exists. Not surprising in these cases, it's just a truck and a person and a wall. But here's where it gets crazy. Think about gravity. Earth pulls student. That's a fact. The earth pulls you down with a negative force. It's pointing down. But what if I swap the nouns here? Student pulls earth. What? No way, man. You're not pulling on the earth. You're not reaching down and pulling up on the earth. You're wrong. This is fact. Gravity is a force that everything possesses. The earth is pulling down on you, and actually you have a very small gravitational force that's pulling up on the earth, no matter how far away. So if you were to somehow fly out to the edge of the galaxy, your body would still be pulling on earth with a minuscule amount of gravity. The reason we can't sense this, the reason you're not actually making the earth move very much, is because your mass is way smaller than the earth's. So everything in the universe pulls on everything with its own gravitational force. You just can't sense it because of the two objects being too far, or because of one object being much larger than the next. So the point is, you can always swap the nouns to get the next force. That's just a really cool example. The earth is pulling you down, and you are actually pulling the earth up. In my opinion, it ain't physics unless we're doing some math. So let's do an example with those equations at the top. A 92 kilogram astronaut pushes a 11,000 kilogram spacecraft with a force of 36 newtons. Calculate each of their accelerations. A 92 kilogram astronaut pushes a 11,000, I guess you'd say, an 11,000 kilogram spacecraft with a force of 36 newtons. And the question is, the prompt is, calculate each of their accelerations. So let's look at the forces. The forces here would be astronaut pushes spacecraft and spacecraft pushes astronaut. Very similar to the Earth example. Although the forces will be equal and opposite, the spacecraft will move less because of how light it is. So let's draw it. Now this will not work if there's more than one force on each object, so we'll assume that there's no thrust going on from the thrusters. And here's the forces. F1 is 36 newtons. Astronaut pushes spacecraft. That means F2 is negative 36 newtons. So I did use the equation here without really showing it because it's kind of a boring equation. It's just an equal sign. So what I did was, this is 36 equals negative F2. To get F2 by itself, I multiply both sides by negative 1, or you divide both sides by negative 1. Same thing. Point is, negative 36 is now F2. So that's where I got that number. So this equation is not really useful for plugging stuff in. Sometimes what we'll do with this equation is we'll plug in MA and MA. So we could, if these are the only two forces, we could write it like this. M1A1 equals negative M2A2. We won't do that here, but it's a good one to know. So what we're really going to use is those other two equations. F1 equals M1A1, and F2 equals M2A2. Now remember what we're doing here. Object 1 is the spacecraft. Number 1. And the astronaut then would be number 2. Maybe I can draw it on his battery pack. Nah, can't really see that. So we'll just put it right next to him. Number 2. So M1 is the mass of object number 1. So that'd be 11,000. And so when we solve, we'll get the acceleration of object number 1. F1 is the force that is, the amount of force that's pushing on number 1. So all we do here is we divide by 11,000 on both sides, and we'll get 0.0033. I think it's repeating. If you want to do, we should be doing, I've always said we should do 3 sig figs or more. So really, I think this would be a better answer, but this is just notes. I think this is a better answer. Okay, so for F2, same thing. We just plug in the negative 36. You can forget the negative and plug it in later. It's not as, physics is not as exact as math tends to be. So when we divide this one, 36 over 92, and we'll get 0.391. So look at that. I forgot to write the negative sign. And you just have to remember what's going on in the problem. It's accelerating left. The number 2, Mr. Number 2 over here, he is being accelerated left, and so this must be a negative. So you should always refer back to your picture and always refer back to this. Ask yourself, are the signs correct? Should this be positive? Yes, because it's moving to the right. Should this be positive? No, because he's moving to the left. That's how I remember to tack on the negative sign. So that's about as tough as the mathematics gets. We're going to look at one more example because it goes back to that crazy concept of gravity, and I think it'll be a good one to close on. I want to write this in a short way. So we're going to calculate the acceleration of Earth. Okay. Calculate the acceleration of Earth I have the number for mass of Earth here, 5.972 times 10 to the 24th kilograms. Ugh, 1,000. I'm trying to go 1,000. Oh my gosh, this is a mess. Here's the point. There's a boulder that's falling, a 1,000 kilogram boulder that's falling, and I want to know what's the acceleration of Earth because of it. So here it is. Calculate this acceleration of our 5.972 times 10 to the 24th kilogram planet. Calculate the acceleration of our planet as caused by a 1,000 kilogram falling boulder. Calculate the acceleration of our planet as caused by a 1,000 kilogram falling boulder. So, let's draw it. Here's boulder. It's being pulled down. So we'll call that F1. And then here's our planet. It's being pulled up. Earth pulls the boulder. Earth pulls boulder. Boulder pulls Earth. So we can kind of take a shortcut with this one based on the way it's phrased and based on what we're given. So we'll use that equation that I showed you before. And here's why. We have all the information we need to solve this equation. We're looking for A2, that's the acceleration of Earth. M2 is the mass of the Earth, which is given. M1 is the mass of the boulder, and we actually know the acceleration of the boulder too. The acceleration of the boulder is negative 9.8 because gravity is the only thing pulling it down. So this is why A is negative 9.8, because it's falling. It's in the air, but we're ignoring air resistance. So here we go. 1,000 times negative 9.8 equals negative 5.972 times 10 to the 24th A2. I'm not going to plug anything in my calculator yet. I'm going to divide this number on both sides to get our numerical answer, our symbolic answer. So as you can see, the negatives are going to cancel. So our acceleration will be positive. Earth is going to accelerate up. And look at the way it's set up. We have, we have a large number on top, but we have an amazingly large number on the bottom of the fraction. So we're going to have a very small decimal because of this large denominator. So we could type that all in at once. Let's clear it out. 1,000 times negative 9.8 divided by, and if you're trying this in your calculator, you should do an open parentheses there, negative 5.972 times 10 to the power of 24. That's called a caret, if you haven't seen it. And that'll be it. Let's make sure I got it typed right. Yep, look good. And as expected, we have a very small number. So you got to be careful when you look at this in your calculator. I see a lot of people that just skip the exponent. Here's what this means. A2 is 1.64 times 10 to the negative 21st. Don't miss that ending part. The E is very important. It means times 10 to the power of. And this is meters per second squared. You got to be careful with scientific notation. What does this mean? Well, here's what this means. It is 0 point, and then it'll be 20 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. I might have skipped a 0, but who cares? That's not the point. All I'm trying to show you is, look how small this number is. When a boulder, a 1,000-pound boulder, 1,000-kilogram boulder, excuse me, is falling, it will cause the Earth to accelerate, but so little that you won't even notice. And on the other side of the planet, there might be other things that are falling that's pulling Earth in the other direction. So of course the Earth will rip in half. No, just kidding. The point is, yes, the boulder is pulling on Earth with gravity, but the Earth is too large to feel it, to notice it, so we won't destroy the Earth by dropping boulders or anything like that. Thanks for watching. Thanks for taking your notes. We'll submit these later this week. Bye, all.